Okay, good to see you all here. I think some of you were here last time. I indeed, so this is not an encore presentation. I'm not going to talk about quantum chromodynamics and the Nobel Prize. That was last time. This time I'm going to talk about string theory, which I'm sure many of you have heard about. It's also a very old story. String theory began 58 years ago and is still going strong, much promise. I'll tell you a bit about my personal voyage in string theory, some of the ups and some of the downs, and where we are today, and what's the promise of this even more ambitious attempt in fundamental physics. So last time I told you about quantum chromodynamics, so let's go back 50 years. That's 50 years ago, QCD was there, and we, at that point, had a theory we now call the standard model. It really should be called the standard theory. It's a theory of all of the subatomic atomic forces in nature. Just about explains principle. Work hard enough, everything we observe in our terrestrial laboratories. So 1970, the middle of the 1970s, this theory was more or less complete. And it was an exciting period because, we had the theory, but its implications, its predictions weren't all worked out. There were my goal was to solve the theory. Now, that turned out to be still an ongoing task, which will probably go on for another 10, 100, 200 years. Physics tackles difficult questions. For example, we still don't know how to describe turbulent fluids after almost 200 years. But at that time, we really wanted to calculate the mass of the proton, the mass of the elementary particles. We can do that nowadays using numerical techniques, using the fact that computers have improved by a factor of 1 billion in the last 40 years. And theoretical ingenuity has increased by a factor of 1 billion as well. So with an increase in computing power of 1 billion times 1 billion, 10 to the 18, we can now calculate the mass of the proton and all of the particles, nucleons, that constitute the nucleus of atoms to 1% accuracy. A very difficult numerical job. My colleagues who do those kind of calculations have been working on for 40 years, and now they can really do that kind of calculation. I wanted to solve it with pencil and paper. That's proven more difficult, but much progress is being continued. But by the end of the 1970s, the standard model, the theory of subatomic atomic forces, was pretty well established. New experiments were confirming the theory. Some of its puzzles were being understood. And I and many of my younger colleagues were getting tired of trying to solve the theory exactly. And another fascinating development took place. Once we had this theory that explained what was going on inside the atom, that explained what was going on inside the nucleus, we could extrapolate. We could say, what if we push this theory to ever higher energies, to ever shorter distances? What would happen? Now, traditionally in physics, if you take a theory like electromagnetism, or a theory like gravity, Einstein's theory of gravity, and you push it to higher energies or shorter distances, everything goes wrong. And which is why we continue to experimentally explore higher energies, shorter distances. In the case of the standard model, That's not what happens. Everything gets simpler. That was the asymptotic freedom I talked about last time. The force between quarks gets weaker and weaker, simpler and simpler. Nothing happens. So people, not me, but some of my colleagues, pushed the standard theory, the standard model, say, what happens if we push it higher and higher energy? And they discovered that the forces, strong force, asymptotic freedom, gets weaker. The electromagnetic force acts in the opposite way, gets stronger. And lo and behold, all the forces seem to converge, come to the same value at a very, very high energy scale. Not only that, the three forces that act within the atom and within the nucleus, the force of electricity and magnetism, the strong nuclear force that we solved, the weak nuclear force which creates radioactivity, these three forces of the standard model all seem to unify, naturally fit together as if there was only one force if you looked at very high energy or very short distances. And all the particles that were part of the standard theory fit together naturally as if they were cousins and brothers and sisters at this very high energy. So people extrapolated and said, okay, at the very high energy, they'll be unified. And it was very easy to construct models, tentative proposals of how they would unify. Not only that, that had immediate implications. As one of my friends said, diamonds are not forever. Protons, the basic nucleus of hydrogen, the proton in unified theories is unstable. And eventually, diamonds are made out of protons and neutrons in carbon. They will decay. They will turn into electrons and radiation. So, but it's okay. Don't worry about your diamond rings. We now know experimentally, as well as the theory would tell us, that one proton will probably live without decaying in a poof of radiation for about 10 to the 30 years. 10 to the 30 years is much, much longer than the lifetime of the universe, which has so far only lived about 13 billion years. That's 10 to the 10. Yeah. So protons, not, your diamond rings will last. Not forever, for a long time. But if you put 10 to the 30 protons together in a big tank, say, of water, every year one of them will decay. And you look for that. That would be a fantastic discovery. And people have looked for years and years and years, and so far they haven't seen any. So it might take longer. One of these days, we hope to see one or two protons decay and learn a lot about the unified theory. But so far, no. In any case, this, for my opinion, is the biggest clue that nature has provided us as to what the ultimate unification of the forces and particles of nature is. It's a clue that you have to go to extremely high energy, extremely short distances, and there the forces will unify. But not just these subatomic forces or atomic forces. The indications are that this is the scale of energies or short distances where gravity becomes a strong force, where gravity becomes a quantum force. Now, you might find that strange, that gravity is such a weak force in the world around us, because that's the only force you feel, right? Yeah! You don't feel electric forces, usually, unless you electrocute yourself. Then you'll feel them. But normally you don't feel the electric force or the weak nuclear force. You certainly don't feel the strong nuclear force, which gives rise to atomic and hydrogen bombs. You don't feel it because most objects like the atom or the proton are neutral. They are composed out of particles that carry charges. The charges are the source of these forces. But in an atom you have electrons, negative charge. You have the nucleus, positive charge, and together they're neutral. So a neutral, the charges cancel. You don't feel that electric force, luckily. You don't feel even more so the nuclear force, because the proton is made out of 3 quarks, and the charges that those quarks carry cancel in the nucleus. So the nucleon has no strong charge, so you don't feel the nuclear force. It's a little remnant of it which holds the nucleons together. You do, however, feel gravity, because there's no such thing as anti-gravity. Gravity is sourced by mass. That's what Newton told us. By mass or energy. Energy and mass are E equals mc squared. And there's no antimatter. There's no antimass. There's antimatter, but it carries the same mass. So you can't shield gravity. And if I hold this, what can I hold up? I can hold this up. So think about it. This is being pulled on by every atom in the Earth. The Earth has about 10 to the 26, a billion atoms. And every one of them is pulling on this bottle. And I'm holding it up, little old me, with a little bit of electromagnetic force. Atomic forces come from electricity and magnetism. That's what gives the force that holds this up. Little me with a little bit of energy, force, and holding up this thing which is being pulled on by a billion atoms. That's a very weak force. It is completely so weak that it's completely ignorable. We can forget about it when we do atomic physics. It's 40 orders of magnitude weaker than the electromagnetic or nuclear force. We can ignore it, unless there happens to be a big planet around, then we can't ignore it. So, what happens at very high energies or very short distances? Well, the source of gravity is mass. Mass is just the energy of a body when it's not moving. When it's moving, the mass of the body gets bigger because it has energy. The more energy, the bigger the gravitational mass. So if you take 2 protons, which feel a very weak force between them, totally ignorable, and you make them move very fast, they have a lot of kinetic energy, a lot of mass, the force between them gets stronger and stronger. And at these very small distances, where the other forces of nature appear to converge, gravity becomes equally important. And then we have no idea how to treat gravity, because our theory of gravity, due to Einstein, ascribes the force of gravity to the dynamics of space-time itself. And if we try to take Einstein's theory and extrapolate it to very high energy, very short distances, the fabric of space-time itself breaks down. Space-time itself fluctuates quantum mechanically, is so complicated and curved and that we have no idea what's going on in Einstein's theory. So the clue in the middle 70s was the other forces of nature that are strong and act within the atom and the nucleus converge to some kind of unified theory, maybe at very short distances. at the same point where gravity becomes strong, suggesting that it too will be unified in some way with these other forces. So that began to drive a goal which I and most of my colleagues in the game to try to construct a unified theory of all the forces that we know about in nature. But how to do that? And of course, we weren't in a position to say, okay, we don't know how to do it, we're just theorists. Let's look at nature. Nature can tell us how to do it. But we don't have the ability so far, and today as well, to probe directly, experimentally, and look with a good microscope and see what's going on at these very short distances. But by the end of the 70s, personally, we got tired of the failed attempts to solve quantum chromodynamics with pencil and paper, and turned, like many of my colleagues, to trying to unify all these forces at very high energies, because there it was a different kind of story. In quantum chromodynamics, the nuclear force, we had the theory, we had the equations, they were just too hard to solve except numerically. In the case of unification, we had a goal, we had gravity, which didn't work, didn't fit in. That was a clue. Somehow you had to do better than Einstein. Not an easy task. And you had to unify them with the other kinds of forces. A lot of developments in our theoretical tools were happening, especially something called supersymmetry, a great generalization of the notion of symmetries. And by the early 80s, many of us had put quantum chromodynamics, the nuclear force, aside and said, let's try to unify the other forces with gravity. Now, there was an attempt that had been around even before the standard model, the standard theory, called string theory. That, as I said, is 1968, 56 years ago. People, in trying to understand the strong force, the nuclear force, saw in the data, in the experimental data, indications of what later has turned out to be stringy behavior. As if we now understand within quantum chromodynamics that if you try to separate a quark and an antiquark, the flux, the lines of force get squeezed into a tube, and so a quark-antiquark pair behaves sort of like the ends of a fat string. They were then led mathematically to construct models of this basic force that turned out to be, understood some years later, string theory. A theory in which the basic constituents of matter were not point-like particles, atoms, but extended like strings. So a string is an extended object, and it can wiggle and vibrate. Many different forms. It's much more complicated than just a point. String can move. But it turned out that there was in trying to understand the nuclear force, they ended up with a theory of these fundamental strings with ends. And that was very exciting. Back in the day, I spent a whole year caught up in the excitement and worked on it. I realized that couldn't explain the strong nuclear force. So I went on to QCD. And when QCD came along, the theory of the nuclear force, and was accepted, people dropped string theory because it didn't work. On the other hand, people, in developing this theory of strings, a few things happened that they weren't expecting. It turned out that to make sense of string theory, one, you had to include gravity. Nobody wanted gravity. It was the theory of the nuclear force. What's gravity? But you had to include gravity because open strings could close. And you had to, for consistency, consider closed strings with no chords at the end, just closed. Nothing. Those turned out, remarkably and not anticipated, to have the properties of gravity. They're force carriers of gravity. Furthermore, it turned out that you could only make sense of this theory if there were more dimensions of space. We have 3 dimensions. You can go that way, you can go that way, or that way. Only 3 dimensions of ordinary space. But string theories only made sense in 26 dimensions of space and time. Or, once you included this supersymmetry, 10 dimensions of space and time. But that's enough to kill the theory, because clearly there aren't any more than 3 dimensions. We can see that with our own eyes. However, ever since early with Einstein, shortly after Einstein said space is not just, a coordinate system fixed there, it's a dynamical object, then it can curl up. You can have one of the dimensions not just be a straight line that goes on forever, but a little circle, and then maybe if it's small enough, you don't even see it. So it was understood that you could have 22 new dimensions, or in the case of superstring theory, you could have 6 more dimensions if they were curled up. But that's pretty bizarre, and it took a long time to accept that and make sense of that. But string theory survived QCD. There were a few people, maybe 6 or 7, including my old roommate when I was a graduate student, John Schwartz, and others, but not many, who continued to work on this mathematical physics of strings in 10 dimensions over the years. And but not very many people followed this. There was, however, by 1984, John Schwartz and his colleague Michael Green discovered an aspect of superstring theory, actually really just supergravity theory, that was very exciting. They discovered that such theories might contain the possibility of uniting all the forces in a way that might contain, or are well established by then, standard theory. There was, however, wasn't complete, but that idea was enough to inspire some of us who were trying to unify all the forces with gravity that maybe the right way is with string theory. Now, for me, this was very good news because I'd been working on string theory way back and had gotten interested in it again. And so there was what is now called the superstring revolution of 1984, a very exciting time. The 2 centers of that revolution were actually Princeton, where I was at the time, and Santa Barbara. In Princeton, I was going to teach a course, advanced topics course, maybe on QCD or standard model, who knows. But this development happened, and I decided to teach an advanced topics course for graduate students on string theory, because I knew something about string theory from the late 60s. One of my colleagues and my 3rd student, Edward Witten, was So my first student won a Nobel Prize with me. My third student, Edward Witten, won the mathematical equivalent of a Nobel Prize. He is a supreme mathematical physicist, and he won the Fields Medal, which is, I think, the first example of a physicist winning this famous Fields Medal, which is sort of a Nobel Prize in mathematics. And he was very interested in string theory. And we formed a kind of nucleus of a resurgence at Princeton, where there were many postdocs and graduate students and faculty. Only a few of them knew anything about string theory, but they were very excited by these new developments. Santa Barbara, at the same time, there was our colleague Gary Horowitz, who is still here, Andy Strominger, who was one of the people who recruited me to come to Santa Barbara some years later, and then immediately went off to Harvard, which I'll never forgive him. And Joe Polchinski, our esteemed colleague who tragically died a few years ago of a brain tumor, a great figure in string theory. These were two centers. Throughout the rest of the world, there were only a handful of people who knew anything about string theory. But they all got excited when a few of my younger colleagues and I found a new kind of string theory. We call it the heterotic string. I won't explain what that means and why. But it was the kind of string theory that could conceivably explain the unification of the forces that we knew. At the same time, Edward Witten, together with Horowitz and Strominger and a fellow from Texas, figured out how the extra dimensions could be curled up in a beautiful mathematical way that could produce again, perhaps, the standard theory. These two developments, which occurred in the fall of 1984, fell like a bombshell in the community. Because suddenly, instead of just how the hell can we construct a theory of all the forces in gravity, and how do we deal with gravity, which has all these problems, and how do we quantize gravity, all of that suddenly appeared to be achievable. And immediately, which is often happens in physics, where physicists are often behave like ambulance chasers or sheep, whatever analogy you want, they immediately all start working on this project and have been ever since. It was an enormously exciting point because suddenly it appeared like there was a consistent theory that unified all the forces, a consistent theory of quantum gravity, one that could naturally lead to all of the things that we knew were well established within our understanding of atomic and subatomic physics. There was there were five versions of this kind of superstring theory, but we felt probably only one of them, the one we invented, would turn out to be correct. It appeared that this theory, string theory, really a consistent solution of whatever string theory was, had no free parameters. Every parameter, like the mass of the particles, and everything was in principle calculable. It was dynamical. It was not a parameter that you could only measure and not ever calculate. So, wow, suddenly it appeared we were very close to final theory, a theory of everything. All we had to do was work out the consequences of the almost unique theory, perhaps unique. Very exciting. And the promise was enormous. We all felt we're close to the end. We're close to this enormous breakthrough. Well, to some extent, that's still correct. But it turned out to be much more complicated. We were just beginning the exploration of this new kind of theory, and at the level that we understand, there's not just one possibility, but billions and billions and 10 to the 500 or more different possibilities for these solutions, string theory solutions. So the goal that we as theorists, without any direct experimental, exploration of physics at these extraordinary high energies or short distances, would be able to come up with a final version of this theory and calculate the mass of the electron and calculate everything, well, it's proven to be more difficult. So I sometimes picture, what theoretical fundamental physics is like. Climbing a mountain in the dark, blindfolded, with the fog of Santa Barbara surrounding you. What do you do when you're supposed to get to the top of Mount Everest in the dark, blindfolded? You walk up. That makes sense, right? You want to get to the top, you walk up. You can tell where up is, so you walk up. That's what we sort of do in fundamental physics often, especially in pushing beyond where experiment gives us direct clues. And that's what we were doing back then. And we pushed up, and we got to this peak. Wow, we're up here at the top. Looks great. We can see all sorts of wonderful stuff there if we can only get there. Then we see another peak, like we climbed K2, and far off we see Mount Everest. And that's sort of where we are now. In other words, we know there's this other big peak there, Mount Everest, but we're here on the local peak. It's enormous. We can see all these things. We can learn about a lot of the valleys below. And we have over the years. But how do we get to that peak up there? Got to go down and around. And that's what it's like. Now, so this was 40 years ago. 30 years ago, a new vista opened up where we discovered that string theory, this new kind of theory of extended strings, is not different inherently from particle theory with point-like particles. And in fact, in many situations, the same physics can be described either by the particle quantum field theory tools we use to construct the standard model, or string theory tools. They're dual, we call them dual descriptions of the same thing, the same physics. Sometimes the stringy picture is easier to work out. Sometimes the particle picture is easy to work out. Sometimes, and which gives us confidence in this duality, both can be used, and we can test this duality by getting precisely the same answers. And that's now been done over the last 30 years, thousands of different examples. So now we realize that string theory is just part of a bigger framework of fundamental physics, which in my opinion, we haven't at all yet fully explored. And that both are different ways of exploring the strange and beautiful and yet understood by any means quantum nature of space and time. More and more, we're beginning to understand that our naive, even after Einstein, notions of space and time need to be replaced by a much more sophisticated version that we're working out in simple examples, illuminating many of the paradoxes of quantum gravity, of black holes, but we're far from understanding it. And that deep understanding of the quantum nature of space-time, what is space-time made of, is going to be necessary to reach that ultimate peak and answer not just the unification of the forces, the original goal, but now we realize if you could do that, really, you would have constructed a quantum theory of space and time. What that means is a theory of the universe from the beginning to the end. The universe is space and time. And a solution of string theory, or what will string theory will evolve into, the solution will be a theory of the universe from its beginning in time, whatever that means, to the end, whatever that means. And that's a tall order, one that physics has never been required to ask before, and we have no example even of tentative answers to such a quest. So the problem has become harder in a way, more paradoxical, but our vision has expanded enormously. And we got to find a way to the top of that peak. We do it, we can. And hopefully some of the answers will appear while I'm still around to enjoy them. Thank you.